Welcome to the Soil CRC's Building Technical Capacity for Improved Soil Management webinar series, Managing Soil Constraints. In this video, New South Wales Department of Primary Industries Dr. Ehsan Tavakkoli provides a deep dive into how soils become sodic and how that limits crop yields, as well as identifying and managing sodic soils, comparing a range of novel amendment methods to improve soil structure and overcome soil constraints for improved plant productivity.
I thought what I'm going to do today, so based on the information Felicity gave me, I saw a major interest on soil and subsoil constraints, and basically this was about sodic and saline soils and acidic soils. So for the first maybe 20 minutes, I'll talk about saline and sodic soils. What are they? How they actually form in agriculture. My research is mainly focused on broad-acre cropping system, but the concept of sodic saline soils, their amelioration and management is pretty much the same for either you're in the sugarcane industry or horticulture and so on. So I think if you understand the concept and what is the problem, then we can find a solution for it in different farming system. So very quickly, I just want to talk about the distinguish between a saline soil and a sodic soil, because this is what is mostly confused even in science these days. I use the broader concept of salt-affected soil. And under that umbrella of salt-affected soils, we have so many different categories. The soil can be saline, sodic, it can be saline and sodic, and then you have a complications of pH influence there, which makes that management of these soils also very difficult, because it's not just one single problem. It's a number of different issues that needs to be tackled at the same time. So basically, if you look at the left-hand side in this image that I put and written a saline soil. A saline soil is saline when you have soluble salt in the soil solution. Okay, so sodium chloride or different forms of salt. It doesn't need to be either sodium or chloride all the time. It can be, calcium, magnesium, and different carbonates in the soil. When you have them in soluble form in the soil solution, the soil is becoming saline. And when that soil is leached by rain or irrigation over a number of decades, some component of that salt can leach down into the deeper soil profile. But in this case, when you see in the sodic soil, the sodium can remain within that clay aggregate. And in the next couple of slides, I'll explain this in more details. But when you leach out that salt and the sodium stays in the clay, the soil is becoming sodic. So that is no longer a soluble salt, but it's a salt that is being incorporated into different plates of the clay in your soil. And the problem and how the crop feels the pain is completely different. So I just wanted to set that difference between a saline and sodic soils, and from now on, I focus on what are the differences. Just imagine if you have a clay particle and that brown large circle on the left-hand side. That clay particle is usually negatively charged. So, and for this clay to bind together, you need to have a positive bridging between the clay particles to make that binding. Okay, and that's when you have calcium, magnesium, sodium, and different cations that form that bridges. Each of these elements have a diameter and a strength, atomic strength, that making the binding. And if you, for example, remember when we were kids and growing up, our moms were encouraging us to drink more milk because of the calcium in milk. The calcium plays for the bone structure. Calcium plays a very similar role in clay particle. you want more calcium on the clay. This is not in the soluble form, this is on the exchange side. You want that calcium on the clay to have a better structure of the soil. And in comparison, when your clay is dominating with more of the sodium, which is a lot smaller molecules, then the bondings are a lot weaker. And when they are weaker, the soil is not stable. That's when you have a structural issue. What is the issue in a sodic soil? On the left-hand side, on the right-hand side, you see a petri dish where there is a brown liquid. That is a clay that is in contact with water. Because that bonding, those sodium, too much sodium in the soil, the bondings are weak. The clay, which in a normal situation should be stable, is actually slaking and dispersing in the soil, and you have colloidal dispersion in the solution, which can cause problems. What's the problem? These are tiny, tiny colloidal particles that at the landscape, if you have many hectares of this sodic soil, what happens is that as the soil dries out after the dispersion happens, those fine particles can sit like a cement. That's where you get surface crusting or blockage of the soil pores. Imagine if the rain or irrigation water is going to penetrate or infiltrate into the deeper soil profile, and you get waterlogging. The reason for that is that this cementation or hard or the surface which is dispersed clay after it dries out, preventing that infiltrations to happen. So in a sodic soil, we often have a major soil structural problem. I want to simplify this for you further. So just imagine on the right and left hand side, you have two clays. Yeah. So it's just a bit of soil in your hand. As I mentioned, these are negatively charged and they need to be connected to each other to form a structure that is your soil and for the crop to go through it and the water and nutrients. In the middle, you need a positive charge to bring this together, right? So you need a positive charge to bring the negative soil clay together. And the cation that does that can be calcium, potassium, sodium, or magnesium. When you have a large amount of sodium as that positive charge, you have a sodic soil relative to your other cations, such as calcium, magnesium, potassium, which are stronger in bonding. And that's where the problem happens. Why? Because the proportion of that sodium on the soil particle is basically providing that really weak bonding of soil aggregates, and you need to add an amendment such as gypsum, which is a very common product in agriculture, to compensate the amount of calcium that you needed to have on that soil, and it's not there anymore, for the sodium to come off the clay, so it's exchange, for the sodium to come off and replace it with calcium so you can improve the soil structure. This is the concept of a sodic soil, and really, if anyone has a question now, I think it's the best timing to answer, because I really want that concept to be spot on in our understanding. So there is no salinity issue in this example. It's just the soil which is sodic, and it has a structural problem. Salinity is more a chemical problem that I will explain it later. So again, a little bit of more thematic presentation of what the problem is. On the left-hand side, you have a dispersed clay because now this clay is hydrated and there's no structure. Whereas when you have flocculation, which is the term opposite to dispersion, those clay particles that are well structured because there is enough calcium and organic matter in the system, they stay together and form a soil structure. When the rain or irrigation comes through, on the right-hand side, the water will easily go through the soil pores and the roots also will go into the deeper soil profile. However, when you have dispersed clay, you get that waterlogging events in this case, and the water infiltration or soil hydraulic conductivity is a lot more reduced. So this is the problem that you want to improve, which is a lot actually more difficult than many other constraints in agriculture. So how to identify this in the field? Yeah, I think the first step is very simple. If you think you have a sodicity problem, and by the way, what I really need to mention right at the beginning is that the term sodicity is a very general, arbitrary definition of the problem. Dispersion is really what we are after. We want to identify if our soil disperses or it doesn't disperse, because you may have a situation that according to your soil test, your soil is sodic. However, if that sodic soil doesn't disperse, which it can happen, it won't respond to gypsum. That's when a lot of people ask me, oh, okay, so based on the soil test, my farm is quite sodic, but there is no benefits of gypsum application. In most of the cases, that happens because the soil, even though it came as dispersive, it wasn't actually, the soil was sodic, it wasn't actually dispersing, and it is the dispersive nature of the soil that is responding to gypsum application. So in the field, if you want to identify it, it is very simple. You just need a few petri dish or even a plastic jar or a cup, and you need clean water, and you need a few aggregates of your soil that you suspect it has a problem from different depths and across the paddock. All right. So because it's very variable, you need to have a good understanding of the variability of this problem. You put the aggregates into the cup, you add the clean water, and after an hour, if that cloudiness, that milky cloudiness around the particle appears, then you know you have dispersion in the soil. Whereas, as you can see, those aggregates that sit there in the petri dish intact, they are not actually, they won't need any gypsum application. And that's the problem, because most of our dispersion these days is happening in the topsoil, according to these different depths, 0 to 10, 10 to 20, 20 to 40. You will see that the topsoil is actually not dispersive, and it is the subsoil that has that problem. And if you leave or apply your gypsum in the topsoil, you will still have the problem in the subsurface, in the subsoil, and you didn't have any gypsum requirement for the topsoil anyway. So, and that's where you need to be having a good idea of what is the problem. After you identify you have dispersion, then you do a soil test, because that soil test in the lab will inform us how much gypsum is required to be applied into that soil. The first petri dish test is just observation. The second soil test is to give you the prescription of how much of what material is likely going to fix the problem. I just give you some other example. This is just different soil types from southern part of Australia, Walga, South Australia, Victoria, in those long columns that you see. Simply, I just mix 100 grams with a few hundred mils of water. You will see the first 4 are quite dispersive, so you have that cloudy, milky solution after we mix the soil and water together. And the right hand side column is very clear. However, that soil test was actually 40% sodicity there. The reason for that soil that is sodic but not really dispersing anymore is because that soil at the same time is very high in salt content. And that salinity, most of our saline soil has a good structure. When you have a saline and sodic soil, the salt concentration fluctuate that amount. It's like a gypsum. Gypsum is a salt you add it to the system, so that dispersion actually reduces. And if you just go based on this an ESP test at the first place and apply gypsum, only the first 4 soil will respond to gypsum application, and the last one doesn't need any gypsum application because it's not dispersive. Those smaller test tubes on the right hand side shows what gypsum does to a dispersive soil. So starting from a sodic dispersive soils from the left hand side all the way to the right hand side, we increase the amount of gypsum addition, And what happens, as you can see, the amount of dispersion is actually settling down. And this sort of test can tell us at what concentrations of gypsum we actually fix the total amount of that dispersion. And we can also, based on these studies, decide how much gypsum is needed to be added in the field. Okay, so from this first few slides, I wanted to set the point of what sodic soil is, how we test it in the field, what needs to be done after that in the lab, and what is actually the effect of gypsum when people say we need to add gypsum into the soil. We need to reduce that dispersion in the field. Okay, so this was a very simple overview of the problem in the field. However, if you think about what are the soil or subsoil in our farming system, I can categorize them into two categories. Chemical constraints. We have acidity, sodicity, alkalinity, because high pH itself is always a problem, and also salinity. And we have compaction, that Meran will talk about it. And there are waterlogging issues that are interrelated to the sodic or structure. Because if you have that dense clay, you get transient waterlogging, which is a physical problem that is associated with the chemistry, which is that sodicity and high dispersion level. So this is the simple way. However, the next graph will make everything more complicated. This is the reality. This is what happens in our farming systems every day. Because if I want to take into account each of these soils can have three different pHs. They can be acidic, neutral, or alkaline. And you have a non-salt affected soil on the bottom left-hand side. And then you have a saline soil or a saline sodic soil or a sodic soils. And what you need to do, or all of us we need to do in our farming system, is to understand where in this chart we are sitting. Do we have a sodic soil with a pH of less than 6? With a pH of more than 8? Because if the pH of a sodic soil with an alkaline pH more than 8 is our case, which is actually the case for most of our farming system, we have a few issues. We have soil structural issue. We have that dispersion. We have waterlogging every now and again. We have carbonate and bicarbonate toxicity, because that alkaline soils are characterized by high carbonate toxicities. And you can also get some sort of deficiencies of nutrients. And just adding gypsum into these soils is not going to fix the problem. So I call that a multiple subsoil or soil constraints, which we need to correctly characterize what the issues are and what depths can that be achieved. And if we can manage the soil to achieve productivity improvements, then we can go ahead. Otherwise, it is very risky. Soil management is expensive, and we need to make decisions based on minimizing risk and return on investment. So the point of this graph or this diagram is to just highlight what a complex problem is subsoil and soil constraints when you interrelate the pH, salinity, sodicity. And I think at some stage I came up with 16 different categories of these soils. But we can actually shorten them or summarize them into some really key ones. And I'd like to focus on alkaline sodic soils for the rest of this presentation, and into this, and also the alkaline saline soils. Most of our acidic soils, you don't need to be really worry about sodicity, because the pH, the high pH in sodic soils is one of the reasons that we get that dispersion. Okay, so acidic soils in comparison to these are less, they have less chance of dispersion. So if I want to quickly talk about distribution of sodic soils in Australia, of course, there is a wide range of cropping system all the way from the northern region to the southern region and western region that is that have this problem of sodic or subsoil or topsoil. And then in terms of grains industry, the yield gap associated with the soil constraints is basically anywhere from 0, where there's no problem, up to 0.4 ton per hectare per year. So if I add all those values based on the recent study, every year we are losing about $1,300 million per annum just because of the specific in Australia across the whole northern, southern, and the western region. And so it's a significant figure in our yield gap. So this is the potential that we can achieve, and we don't achieve it because what is the major problem in sodic soils and acidic soils, or wherever you have a soil constraints problem? You can have a waterlogged system, you can have a crop establishment issue. There is one factor in common between all these problems, and that is the poor water use efficiency. The concept of the work you want to do and you want to develop a management for is to improve the water use efficiency of these systems, because if you imagine you have a profile of water that your crop should effectively dry that out from, and so this is your soil profile at the beginning of the season. I call it the upper limit and the lower limit. If the plant have access to this profile, you will have a perfect yield at the end of the season. However, when you have a subsoil constraint in your system, that bucket size is much reduced. Okay. What I like to do in our work with the subsoil constraint is to improve the bucket size, or the plant available water, which is potentially available, but the crop can't see it because of that soil or subsoil. There are a few options to achieve this. We can achieve it by soil management, and you heard probably about some of our work on subsoil manuring, or adding organic amendments, or combination of organic and inorganic amendments into the subsoil to improve that poorly structured environment. We can improve our genetic tolerance. We can come up with new varieties that are better performing in some of these hostile conditions. And the third option is to make new amendments. Obviously, lime and gypsum has been used in Australia since 1920s, and we are still doing research on the same product. One of the reasons that we haven't achieved a lot of breakthrough is that these conventional mine products are not highly effective in ameliorating the topsoil problem. They are good for the topsoil, but they don't really influence the topsoil effectively. So as part of the CRC project, we are actually focusing on the subsoil management, so soil management issues. This is the program 4 under Lucas's leadership. And then on the right-hand side, we are also improving the formulation of the new amendments. Can we improve the mobility of gypsum and lime to penetrate into the deeper soil profile to improve the soil environment? So just I want to give you some encouragement. This is what excites me all the time. On the left-hand side, you see a subsoil from Victoria that is quite poorly structured, dense clay. And after 4 years of adding organic amendments into the soil, you come up with a subsoil which is a lot more well aggregated and transcutaneous structure. So there are quite a lot of potential there. And these changes in the soil structure has been associated with up to 70% increase in yield for up to 10 years, right? So there is, like, often you need a one-off application, and the effect lasts for a number of years, depends on the environment and depends on what you're adding into your soil. I'll give you some case study. I think I'm running out of time, and I've got quite a lot of slides to go through, but I'll go very quickly. Felicity. So this is an example from southern New South Wales. Okay, so we've got a property that has a pH of about 5 in the surface, and as you go into the deeper soil profile, that pH goes up to 9. So this is a classic, actually sodic dispersive soil that, even though the pH in the surface can be neutralized, as you go into the deeper soil profile, the pH increases by depth into extreme alkaline condition, and that pH itself can cause a problem because of that carbonate and bicarbonate toxicity. Then the ESP, which is your exchangeable sodium percentage, this is an indication of how sodic your soil is. Um, and in Australia, anything above 6% is sodic. Okay. You can see that we have a non-sodic topsoil, and as you again increase, as you go down to the soil profile, the sodicity or dispersion increases up to 35%. And this is what I'm talking about. So most of our topsoils can be either looked after or they are not actually sodic or alkaline. So it is the subsoil that is my interest. And that ESP itself has problem with poor structure, waterlogging, and some dispersion. And salinity here, which is electrical conductivity, again, in Australia, anything above 4 considered saline. It's about 6 or 7 when it hurts the crop, like wheat and barley. And basically, you have osmotic stress or some sort of sodium and chloride toxicity symptoms. And as you also can see in these petri dishes, the topsoil is not dispersive. As you increase the depths, it can be dispersive. Okay, so what we've done here in this case, we tried a number of different amendments. We wanted to fix the topsoil. Okay, so the topsoil, even though it's okay, most of the farmers would apply the gypsum to increase assuming they increase the productivity. But if the soil is not dispersive, no gypsum or no amendment is required. It was my interest to see what are the possibility to fix that subsoil. And quickly, I run you through some of the treatment views. Of course, gypsum is one of the most commonly used amendments in agriculture for amending sodic soil. In addition to that, I wanted to see if organic amendments, a manure or a plant biomass, this can be as simple as a wheat stubble or legume stubble after your harvest, because it's very rich in carbon. Can we incorporate that into the subsoil and let the microbial decomposition of that stubble to help the soil structure by adding the carbon and some nutrients in that subsoil environment, which is poorly structured. Because in sodic soil, we have a structural issue that the structure needs carbon to bind the aggregates together, in addition to gypsum that fixes the dispersion. So we have actually a couple of issues here. So we had here a number of different treatments, from manure, from pea straw, from just nutrient itself, because the subsoil is quite infertile, and we wanted to see what are the possibility to make changes in this hostile subsoil environment. We used a machinery, a deep repair that is fabricated and designed in DPI New South Wales. With this machinery, we can apply organic amendments up to 20 tons per hectare. We can also add lime or gypsum from this box. And then in front of this hopper, there is a liquid tank that we can apply liquid fertilizer if we want to at the same time, or as just on their own application. Okay, so this is the machinery that we used, and it has 5 tines, and the rip lines are about 50 centimeters apart from each other. This is an aerial photo of the trial in 2019. Remember, this experiment was set up in 2017. We had a barley crop in the first year, then we went to wheat crop in 2018, and then we went to canola in 2019, and now we are back into wheat in 2020. Very quickly, I just run you through the data from 2019 season, that some of those amendments, such as deep manure, deep gypsum, and deep pea hay, which was a pelletized product, plus NPK, resulted up to 36% increase in yield. This is the absolute yield. Relative, these numbers on top of each bar is relative to control, which is on the left-hand side. So what I really like to use my time wisely, because I know I don't have much, is to actually explain what happens after you add some of these amendments into the soil. Before going to that explanation, I also wanted to give you some idea of what happens in the second season in 2018, which was a very dry season, if you remember, at least for New South Wales and southern parts of Australia. Again, some of those deep applied treatments, which is a combination of organic amendments and not necessarily manure. This is just simple pea hay plus gypsum plus NPK, resulted up to 53% increase in yield. So the message here is there are potentials or significant potential to improve productivity if you are managing your subsoil. And it's a one-off application there that you need to choose wisely what you need to add. So first thing that you're looking for in this environment is whether we change the bucket size and that concept of the plant available water. What is going to affect the bucket size is the soil structure and also the amount of root that is now going to be in the subsoil affected by this management. If you don't have more root to take up more water, you cannot have more biomass and you cannot have more granules. We do some tests in the field looking for the root accumulation in the subsoils affected by different amendments. If you look at control on the left-hand side and some of the treatments on the right-hand side, you will see we have a significant increase in the amount of root in that depth of 20 to 40 centimeters after 3 years of placing the organic amendments into the subsoil. Okay, so that extra amount of root there means they have more access to the water, and if the water is going to be there, okay, so that's the trick. You need to have remaining water into the subsoil, and you need to improve the soil structure to release that water, because if you don't release it from a dense clay, even the root is there, you won't still going to see that. So in our root studies, we have a strong evidence at the moment over a number of years that we have a significant amount of extra root. And we also have evidence that we have a much better hydraulic conductivity in our soils. And the hydraulic conductivity is the capacity of the rain to penetrate to the deeper soil profile, because you want to improve that waterlogging condition if you experience it. Even then, you still may have water storage issues. So we do in-field hydraulic conductivity studies, and very similar to our observation with the roots, you will see that the deep placement of organic amendments improve the hydraulic conductivities quite significantly over a number of years. So that means you actually store or improve that dense clay to let more water to go into the subsoil. Okay. And this measurement here is how much water is being taken up by the plant. Okay, don't worry about the complexity of this graph. Just focus on, please, on the fact that if we are shifting to the left-hand side of this graph, the plant is taking more water from the subsoil. So these two bars are control or deep nutrients, where we just put nutrient into the subsoil compared to doing nothing. And you will see that both of them are quite similar in this and in the lower soil profile. When you start looking at deep organic amendments that we left into the subsoil, you will see that there is a shift. About 10 to 15% are calculated across all these treatments. There's about 10 to 15% extra subsoil water is being used, and that is an indication that we improved the soil structure and the crop had the ability to take up that water. And a back of envelope calculation there is for an extra 10 mils of water, if you make that available and the crop has access to it, that's about 0.5 ton per hectare of extra granule. Okay, so that's the conversion based on modeling. And if I want to summarize that, what happened to the soil that we can see these differences, if you just look at the pH, remember the soil had a pH of about 9. When you add gypsum to this soil, the gypsum is reducing the pH quite significantly. So what you want to achieve here is to get rid of all the toxicity of the carbonate bicarbonate in this region, and by reducing the pH, you're also improving the dispersion. Then you add organic matter, but organic matter doesn't do anything with the pH. It's just the gypsum effect that is making an influence. In terms of the sodicity, you also see a very little reduction in the soil ESP by adding gypsum. Again, organic matter doesn't have a major influence. So far from the chemistry point of view, we are just dealing with the effect of gypsum. In biology, however, when we measure carbon in the soil, you will see it's exactly the opposite trend. Gypsum doesn't play a role there because there is no carbon in gypsum, but it's organic matter that has a huge amount of carbon that in this case is actually in the soil fraction. So this is a measurement of how much carbon is in different soil fraction, and that carbon can be blue for improving the soil structure. If I measure the soil structure in the field, you will see a fourfold improvement from the control to some of our best performing treatments. And we started to see in the field some biological activities and deeper root penetration, infiltration in these conditions, which is quite encouraging because if you look at on the right and left-hand side of this drip line where the amendment is, there is no activity or there is no presence of root. It is where the amendment is being placed. And that's a strong message because there are windows of opportunity here to fix or to improve, not to fix, to improve some of these hostile conditions. So, and some more visual observation. This was taken in September 2018, which was a very, very dry spring. And it's a comparison between your control on the right and ameliorated area on the left-hand side. And I just took a few crops from each of these locations, and you can see the vigor and the health of the crops are quite significantly different from each other. Again, more encouragement on what can be achieved in these soils. So to summarize that Sodic Saline presentation, just from the management point of view, from the last few slides, I think the deep place of organic amendments and gypsum significantly can increase the yield. We observed the better root growth. We also improved the infiltration rate and crop water use. The mechanisms, as I explained, pH of highly alkaline soils needs to be reduced, and that is a mechanism that we always suggest gypsum is operating. It's not just about calcium, but it's about the pH effect of gypsum. Organic carbon in soil fraction improved up to 4-fold improvement in the soil structure. So if it's a multiple soil constraint, if you have dispersion, sodicity, and a poor structure, you need gypsum for the dispersion bit, you need carbon for the structure. So the message is not just a simple gypsum application alone is going to fix all the problem. The message is you need a bit of carbon in the system in form of amendments, in this case, to improve that structure. There are two issues here. If you're talking about the surface soil application, and that means you have a surface soil dispersion, basically the best answer to that is the crop performance. If you start to see a decline in your crop establishment or crop performance, then that is the time that you need to apply gypsum again. In terms of the subsoil constraint, is a very difficult story because there's nothing that can actually measure that when gypsum needs to be added again. But I would say surface crusting, crop germination, and crop overall health at the early time of the crop growing season is the best determination of when gypsum needs to be applied again. And it's in a few years' time. It's not something that we need to add every year.
Thank you for watching. If you found this information useful, there are many more related projects to discover at our website. Please like this video and subscribe to our YouTube channel for more Soil CRC webinars, project updates, and conference presentations. This webinar series was produced by the Soil CRC, jointly funded through the Australian Government's National Landcare program, to build the technical capacity of natural resource management agencies, Landcare and grower groups to deliver soil health information to farmers for improved soil management. For more information about our projects, visit soilcrc.com.au.